Hello, everyone. Welcome to this week's modules video. This week, you guys learned about correlations, how correlations differ from causation, and all of the knowledge related to understanding how we can differentiate or infer what is causation versus just a mere correlation. And in this video, you will learn how to run correlation, how to analyze correlation using R. So all the information, all the instructions are in practice and applications, right? So here we are returning to our file because we only need the composite variables, which we made averages of all the scale items. So as now you might have kind of got a sense of it, most of our analyses follow the same procedure. We first install the necessary R packages, and we use the package functions to run the desired commands that we need. This week, we're going to run correlation, and we're going to visualize the correlations. And then we interpret the outcomes, and then you copy and paste all the information on a Word file or a text file, and then you submit it, right? So that's what we're going to do. We're going to compute correlation coefficients. We're going to interpret the results, and we will create a correlation matrix and visualize it and generate scatter plots because it visualizes the relations between the two variables, which gives us more information than just looking at the numbers. And also, we're going to create a lot of plots today. And then you're going to create a APA style correlation table, which RStudio can do it for you automatically. So as of now, you might have kind of got a sense that there are so many R packages out there. So it makes it very easy for us to run any type of analysis because most analysis that are developed are available on R packages. Since R is an open source kind of language, everybody can make all different kind of packages and some get really popular. And there's a lot of popular packages for visualization and correlation, so we will use those today. So let's get into the actual data analysis. First, we got to load the data set on and all the necessary packages, right? So you should have already installed the read Excel package. We already have that. So let me copy and paste all the other packages that are new to us and run this command. So this is going to be used for correlation visualization. This is for scatter plot. This is for pairwise plots. And this is to create APA style tables. So I'm going to drag and select all of them and run it. It will take some time to install all the packages. Uh, so be patient and bear with me here. So now all the packages are being installed. So let's wait for the final one, the AP tables one. It should be installed quickly. Oh, it is successfully unpacked. That was quicker than I thought it would take. Okay, so I told you that we're going back to the file with only the composite scores. So it's already downloaded because we already used it before. So I will import this data set so that it is loaded on our memory, on our computer's memory. So we have the file on our source window. So let me get back to our script. And after you install the packages, you also need to have these packages uh, loaded to our library so that it's in our memory and our studio can run it for us. If it's not in the library, even though you downloaded it, it's not ready. So I selected all the library and I will run this command. So now all the packages are in our library. I'm getting this warning messages because I have an older R version, so you can ignore that. And I already loaded the Excel data set, right? So, and if it's in your documents folder, it'll be easy for you to load it because you can load it right away from the RStudio interface. All right, so there's lots of ways to run Pearson correlations, but since we have like how many variables do we have? One, two, three, four, five, six, seven, eight. Since we have eight variables, we're just gonna focus on these. We're going to designate these eight variables and call it core data. So we're selecting the relevant variables from our data set, right? And we're naming it as core data. Okay. So I can run this first or run it all together. You can just copy and paste everything and run it together. And everything after the pound sign is just comments. So R automatically ignores that. So if I explain it again to you, we're designating that from our data set, from our data file, these variables are included in what we will call core data. And we want to compute the correlation matrix. What we will call the core matrix is a correlation analysis. So COR is a correlation command used in R, and this correlation is from what we have designated as core data, and we're going to use pairwise complete OBS, and this is where we designate that we want complete data sets with all observations. Later on, we will be cleaning our data set again, but right now, I think we have all the composite scores for the eight variables, so we already have a complete data, but it's a good practice to designate how you're going to deal with incomplete data or like if there's any missing observations or invalid observations. This is just a common practice to input. And then what we have designated as core matrix is based on the correlation command from our what we have designated as core data. We can designate the decimal places. So let me run this part first. You can run it all together. Let's just run it all together for the convenience. Let me select all the command, run it, and you can see that we have a correlation table created now for extroversion and agreeableness, extroversion, preseason up, so on and so forth. And you can see that the decimal points are rounded up to the third point. If we have ran this print command without the rounded points, then it will just show too many decimal points. So I don't like this. So that's why I prefer to designate how many decimal points we want. So you can see why we want to choose how many decimal places we want. Okay, so we can see that there's lots of correlations ranging from smaller correlations from zero point 0.1 something to very larger correlation. We see 0.651 here, and you can see that there's a lot of correlations in between. So how do we interpret these correlations? So you already learned that correlations are standardized values ranging from -1 to 1. What it tells us is that if there is one standard deviation change in one variable, how many points of standard deviation will it make change in the other variable? So correlation is bivariate relations between two variables. And in general, we consider zero point 0.1 to zero point 0.3 as weak correlation, zero point 4 to 6 moderate correlation, zero point 7 to 9 strong correlation. But these can vary based on the context. if we're measuring psychological variables compared to industry actual numbers, for example, like numbers of like time and number of inventory in a kind of distribution center, something like that. You have to consider the context and think about what is a strong correlation and what is a weak correlation. But this is just considered a general interpretation of correlations in general. All right, so yeah, and negative values is when one increases, one decreases, right? You guys learned about that. So we have all the correlation values here, but there is a very um, powerful reason to run visualizations because everybody's a more visual learner. We understand things better when it's visualized. So that's why we installed all these libraries for visualization. So let's start with a heat map. We already loaded this to our library. And so GG Core Plot provides a heat map for us. And this is how we want to designate it. We want to show it in circles, and we want to use the color blue, white, red. So blue circles show strong positive correlation. Red circles show strong positive. Blue circles show strong negative correlation, so on and so forth. So let me copy and paste all this and highlight it and run it. Now on the right below side on the plots, you will see this plot created. Let me enlarge this window. And so, yeah, you will see this, right? So the stronger correlation, the more vivid red color it has. So it looks like 0.65 is the highest correlation we have, and we have the 0.12, which is between team ID and extroversion. That was kind of the weakest correlation that I see, and 0.65 between flourish, well-being, and state hope was the highest correlation. So people who have high state hope seems to be happy with their lives. Makes sense. So if you compare this plot with these numbers, you can see that it's much easier to find the higher correlation and the lowest correlations. We don't have a negative correlation, so we don't have a blue color. You can see that it's much easier to identify the stronger and weaker correlations by visualizing it, right? So that's very good. I like that. And that was the heat map. And here's our next step is running specific correlation tests. We want to do this because if we just ask R to make correlation tables and heat maps, it doesn't show whether the relation between the two variables are significant or not. So, and whether it is significant depends on the standard deviations of the measures. So let me show you one example. Since let's see, why did I want to run preseason hope and team ID? Okay, so team ID, we see this correlation with between team ID and other variables. We have relation 7 correlation values here, right? Among these 7 correlation, it looks like the correlation with preseason hope was the highest. So, and I'm very confident that this will be significant because it's the highest value we have. But let me test it by running this correlation test. So this is asking R to run a correlation test. When there's a statistic test involved, there's gonna be a p-value reported for us for parametric tests. So let me copy and paste this to our script. Oops, to the script. And let me run this. When you run it, it will give us a t-test result. The p-value had a decimal point with like 16 more zeros on this. So it's very, very significant, much, much smaller than 0.001. And our 95% confidence interval is that in the population level, what our sample represents, we are confident in 95% that our actual correlation value will range from 0.422 to 0.574. And our current estimate using our sample is 0.502. So we were very confident this is going to be significant, right? But what if we ran a correlation between extraversion and team ID? Let me copy and paste extraversion here. And yeah, let me copy and paste it to change preseason hope to extraversion. And let me run this command. This one was significant when we set the alpha value of 0.05, but the p-value was much larger compared to the correlation between team ID and preseason hope. At a 95 confidence interval, we predict that at a population, this correlation between the two variables will range from 0.018 to 0.217. So it's close to zero at the lower level, but not including the zero. At our sample, it was 0.119. So while it was significant at a 95% level, when alpha level is set at 0.05, we can see that the p-value is larger than the highest correlation, and the confidence interval gets more closer to zero, right? While Team ID's correlation with preseason hope was very far from zero. This one got closer to zero. When you get closer to zero, the the larger the p-value will be. This is a much smaller p-value compared to this one, right? And if the confidence interval includes a zero, so if the lower point is a negative number and if the higher point is a positive number, the p-value at a 95%, the p-value will be larger than 0.05, which means that at a 95% or a zero point zero 0.05 alpha level, it will be non-significant. It will not be significant. Uh, yeah, it will not be significant at a zero point zero 0.05 level using the 95% confidence interval when it includes zero in between. Okay, so by using the correlation test, you can ask R to run all the statistical tests to see if the correlations are significant or not. So looking at bare eyes, it looks like I think most or all of the correlations will be statistically similar. Let me just test agreeableness and team ID just to make sure. It might be non-significant if it has more errors, if it has larger error values. So let me change extroversion to agreeableness. Let me run this. This was significant also. So it looks like if our measures have a good distribution, all the correlations will look significant to me. So that's how you see if the correlation is just an estimate of a number, right? If you want to check if that number is statistically significant or not, we have to run a statistical test. And the core test command is how you achieve that. Now let's create a scatter plot. So the heat map was showing the matrix with colors. Scatter plot gives us information of bivariate relations in more detail. So we already loaded this library. So let me copy and paste this command and run the data. And it will give us a new plot. So we can see that our data is very much skewed to the highest number, but it gives us the slope degree between the two variables. and the range of this slope within a 95% confidence interval. It also gives us the statistical result. It was significant, and it gives us much more information more intuitively. So this is the basic command to show a scatter plot between two variables, but uh, the strengths with new packages is that it can provide pairwise correlation plots with all the variables. So here, when we're just using the scatter plot between two variables, we designated the two variables, right? But we can use core data, which we designated very earlier, right? We designated the core data that we're interested in are these 8 variables. We can create pairwise correlation plot using all these 8 variables. So let me do that for you. Copy and paste the command and run it. Let me run this on a larger screen, larger window, so you can get a better look into it. Let me run this. And it will give us a plot with all the pairwise correlation information together. So you can see that the scatter plots are more distributed for extroversion because extroversion had a normal distribution. Student involvement and attendance intention was very skewed to the left, right? So you can see that everybody wanted to go to the game. Everybody was highly involved at A&M campus. So you can see why the scatter plots are much more dense at the higher numbers because let's look at student involvement and attendance. Attendance and student involvement, student involvement and attendance. Yeah, right here. Right here. Yeah, you can see that there's lines on the top because it's all very skewed data. And you can see that uh, uh, well-being and state hope was very high correlation, right? So you can see that this scatter plot follows a more linear line than the other. And you can zoom and export this plot to take a more closer look at it. So by creating this pairwise plot, you can see the numbers, the degree of significance. You can see that TMID and extraversion had one asterisk, showing that the p-value was smaller than 0.05, but not 0.01. TMID and agreeableness had a p-value smaller than 0.01, but not smaller than 0.001, so it has two asterisks. All others were significant at a p-value smaller than 0.001. That's why it has three asterisks. So we can understand the bivariate relationship among the variables in a single glance. So that's the power of visualization. So I'm very happy with this pairwise command provided by the GGLE package. So that's why I like to use all different kind of packages in RStudio. So it shows scatter plots, correlation coefficients, densities, and etc. So it's very useful information. So based on these results, you can copy and paste it and interpret, find, let me know what was the strongest and weakest correlation. And you can talk about some of the correlations among the variables that you find interesting. It would be good if you would discuss some of the variables that you chose initially to put into your model. So here are the takeaways on how you can analyze data and how you can benefit with RStudio and all the packages. And here's another thing. If you remember, we have loaded this APA table package to our library. There's an awesome thing that it does for us. If you run this command, it is asking the APA package to, oops, I didn't copy the A. Is asking to create an APA correlation table. So this is command inside the APA tables package. With the data is what we have designated before, the core data, right? And the file name that we're asking it to create is APA correlation table.doc. So we're asking, and the table number is one. Uh, this we're asking ours to create a AP style correlation table for us. So if you run this, it's gonna create this file, a new file with this name. So let me run this. So I ran the command, and it looks like these information are created into table one. So go to files, and click home, and then you will see that APA correlation table is created by RStudio. So if you would open this file, you will see that there's a brand new APA table which follows the correct APA style with all the variables for you. And you can kind of change the table width and those things based on your preference. But if you know how tedious it is to create certain publication style tables, I think this is a very powerful tool. So if you have all the variable names aligned correctly and everything uh, set up correctly, it will give you this APA style correlation table. And I think this is amazing that you can just download packages and ask R to create these kind of files for you. So there's so many things to explore in RStudio, and I hope you guys are excited as I am. And let's continue this awesome journey. I'll see you guys on our next video.